Hey, welcome to The Explainer. Okay, so we've got AI that can do some pretty incredible things, right? But it feels like we keep hitting this wall. It can crunch mountains of data, but it just can't learn and adapt with the kind of nuance a human brain can. So the big question is, how do we break through that wall? How do we build an AI that actually thinks? Well, let's get into it.
Just think about it. What if we could build an AI that doesn't need these massive prepackaged data sets? What if it could learn from raw experience, adapting on the fly, just like you and I do? This right here is the promise of what we call brain-inspired AI, and it's seriously poised to redefine our entire technological landscape.
So let's break down the fundamental difference here. The AI we have now, it's powerful for sure, but it's basically rigid. You train it, then you deploy it. That's it. Brain-inspired AI, on the other hand, is fluid. It's constantly learning. We're talking about a huge shift from just brute force data processing to something that feels a whole lot more like genuine intelligence.
All right, so to understand how we actually get there, we first have to talk about why. Why do we keep looking to the human brain as the ultimate blueprint for this next generation of computing?
And right away, you see this huge mismatch. Our traditional computers, they're built on something called the von Neumann architecture. It basically means they process things sequentially, one step, then the next, then the next. But the brain, oh, it's a master of parallel processing. It's handling countless tasks all at once, and it does it with incredible energy efficiency. For the kind of complex, intuitive learning we want from AI, our old one-track mind model is just super inefficient.
So, the first logical step was, hey, let's just try to copy the brain's hardware. And this idea led to the absolutely fascinating field of neuromorphic computing, our first big attempt at literally building a silicon brain.
The idea was, brilliantly direct. If traditional chips are the problem, let's just design new ones that are physically structured like a brain's neural network. The goal was to build that parallel processing and learning efficiency right into the hardware itself.
So how do these things actually work? Well, instead of constantly processing everything, these chips use what are called spiking neural networks. Just like real neurons, they only fire a signal, or a spike, when a certain threshold is met, which saves a ton of energy. And to connect these silicon neurons, they use components like memristors. You can think of them as electrical resistors that have memory to create artificial synapses. This is what allows them to communicate, form pathways, and, learn. And the promise here was just huge. Imagine adaptive robots that actually learn from their environment. Or powerful AI running on a tiny drone at the edge of a network, processing sensor data in real time with barely any power. This felt like a massive step toward putting real brain-like intelligence right onto a chip.
But then we hit a snag. The initial excitement started to give way to this critical realization. Maybe just copying the brain's physical structure wasn't the whole story.
And this became the central question, the million-dollar question, really. For all this clever hardware, were these systems truly getting more intelligent in a way that was actually like a brain? Or were we just building a very elaborate but ultimately kind of limited copy? It turned out this approach had some pretty big hidden limitations. The chips struggled to scale up to the size of a human brain. That energy efficiency advantage, it kind of vanished when they were faced with truly complex tasks. And honestly, our models of neurons were massive oversimplifications of the real thing. It was like we had copied the blueprint, but totally failed to capture the brain's true operational genius. We were missing the software that runs on all that hardware.
And this realization led to a major paradigm shift. The focus moved beyond just the hardware and started going towards decoding the brain's software, the fundamental principles that make it so ridiculously powerful.
Okay, so this marks the big shift from what we call structural to functional emulation. The old way was all about what the brain is made of. The new way, it's all about how the brain actually processes information. It's about using really advanced algorithms to get that brain-like efficiency. And you can often do it on more traditional hardware.
The key aha moment was this. The secret isn't just in the silicon, it's in the code, the principles. And so the search for answers turned to cognitive neuroscience to try and find these fundamental principles of thought. This led to breakthroughs based on amazing concepts like predictive coding, where the brain is constantly making predictions about the world and then learning from its mistakes. But maybe most important, it led to this idea of continual learning. Now, this is what allows us to learn a new skill, say playing the guitar, without completely forgetting how to ride a bike. This is a huge problem for current AIs, which often suffer from what's called catastrophic forgetting when they're trained on new data.
And look, this isn't just some theory stuck in a lab. This new approach, this functional emulation, it's already out there producing some absolutely mind-blowing breakthroughs in the real world. For one, we're seeing generative AI models that are showing what looks an awful lot like genuine creativity. They're composing music or creating art that feels totally new and compelling, and it's because they're built on these principles of how we construct complex ideas.
And in the world of autonomous systems, this means hyper-efficient drones and cars that can make complex, instantaneous decisions in totally unpredictable environments. Why? Because they're constantly predicting and adapting, not just following some rigid set of rules they were given.
And the potential impact on our lives is just profound. Imagine personalized medicine where an AI can process a constant stream of your health data and adapt your treatment plan in real time. This is the power you get from a system that can learn continuously.
So where does all of this lead? Well, as we get better and better at decoding the brain's principles, we are entering a totally new era, one that raises some pretty deep questions about our own cognitive future.
Ultimately, this whole quest is about way more than just better tech. As this quote says, the journey is about understanding the very nature of intelligence itself. As we build systems that learn and adapt like we do, we learn more about ourselves, and it pushes us ever closer to that long-term possibility of artificial general intelligence, or AGI.
But of course, this incredible power demands incredible responsibility. We are now facing some critical ethical frontiers. We have to make sure these systems are developed responsibly. We have to demand interpretability so we can actually understand why they make the decisions they do. And we have to really start defining what our relationship with machines is going to look like when they truly begin to think.
And that brings us to our final thought. As we stand here on the cusp of creating truly brain-like AI, with all its incredible promise and its profound challenges, I want to leave you with this question to think about. What ethical challenge of this new reality worries you the most?